Mm, Okay, Dr. Chan, can we start now?
Shall we? Yeah, I think we just proceed, and as other students and friends come along, they can just join us. All right. Okay, so a very good afternoon, and first and foremost, we would like to extend our warmest welcome to Mr. Chan Chin Boon from
Yeah,
Megas
thank you.
Solutions, yeah, for joining us today, or rather to agree to give this talk to our students and our staff today, and entitled "The Reinforced Soil Structure with Geogrid." And just very quickly, I'll take you through CV of Mr. Chan. He has been in the industry for 13 years. He was a USM graduate with a Bachelor of in Civil Engineering honors. And he's a reinforced soil specialist at the moment. In fact, he's a director with Megas. That is a short form for Mega Geo Products and Solutions, right? All right.
Yep.
Yeah. Yeah, and he's very much involved in the design, the construction, as well as the sales and marketing of the products, geosynthetic products of the company. And a lot of Mr. Chan's work involved retaining wall structures, slope stabilization, ground improvement, especially using geosynthetics. So if you have any questions pertaining to this area, I think Mr. Chan will be a very good candidate for you to direct your question to. So I think without further ado, I'll pass on the floor to Mr. Chan to share with us his talk today. Thank you.
Okay, thank you. So, Dr. Hassana, can you stop? Okay, then I will share my screen right now. Okay. Okay, so everyone can see my presentation screen and can hear me clearly, right?
Yeah, we can hear you.
Okay, great. So we will start right now. So thank you for the introduction, Dr. Jimeng. Today we will discuss about the reinforced soil structures using geogrids. So how it can be constructed, a little bit on the design, some concept behind. So before we enter into the topics today, a little bit introduction from where I come from. I'm from Mega Geo Solutions. As you can see, in short, you can call us Megas, and these are the services that we provide to the market. We are quite active in the reinforced slope construction, including the repair of the landslide using the reinforced soil system. And we do involve in a lot of the ground stabilization, including the pavement optimization, subgrade stabilization, and so on. And we are quite active in doing the retaining wall system, which we use a segmental block, and we call it as a Tensar keystone retaining wall. And this is the brand of the product that we is actually the manufacturer from UK, and they are very, very good. Later on, we will talk a little bit about Tensar as well as an introduction for you. So this is the milestones of Tensar. It was founded by Dr. Brian Mills on 1959. And later on, there are some products we invented, like biaxial geogrid, which is being used for the subgrade stabilization. And uniaxial geogrid, this is the main topic that we want to discuss today, is something like this, which we use it to reinforce the soil structure as vertical as possible.
Mr. Chan, sorry for disturbing you.
Yeah.
Fancy, can you stop your sharing? And Mr. Chan, can you share again your slide?
Oh, okay. All right, hold on.
Francis, can you stop your sharing?
Yeah, Francis got to stop the sharing first. Okay. Then I will resume mine. So we go back to the screen right now?
Okay, yes.
Okay, all right. So there are some certificate from the independent authorities is concerned has been obtained. And in 2006, Tensar International was formed, and following by the Tensar Tri-X Geogrid being innovated, and there are some award being awarded. And all over the world is concerned, we have distributor, we have support officers in different places, including manufacturing plant, which is located in Blackburn, our head office of Tensar, and Wuhan as well to support the Asia Pacific market, and the other factories is in USA to support the North American market. And in the factory is concerned, we do the manufacturing of the geogrid, including two main products, which is one uniaxial geogrid. We form the polymer sheet, a row of polymer sheet go into the machine, punching the hole, applying heat, and stretch into one direction to form the uniaxial geogrid. And for the triaxial geogrid, which you usually use for the stabilization is concerned, it will further go into the other machine, but it's a different type of polymer material, and stretch into the other direction. So the triaxial geogrid is then formed. Today, we are not going to cover the topics of triaxial geogrid because I believe my colleague has shared with you before in the earlier industrial talk. So we will focus in this uniaxial geogrid mainly for the reinforced soil structures itself. So over years is concerned, there are performance and product testing being carried out in the lab as well as the full trafficking trial in the different laboratory, independent laboratory as well. And these are some of the pictures showing the lab, the tests being carried out in the lab. And there are some approval obtained through the network rail, through the BBA for the structures, and then some European assessment document and so on. So all these make us the world leader in the development and supply of the products and solution for the reinforcement for the structures, including the subgrade stabilization for road or the railway track. So this makes us having different type of application available to serve our client, including subgrade stabilization solutions. We have the pavement optimization. We have the retaining structures. Today we'll focus on this topic. Rail track bed stabilization, embankment foundation system, and there are some products on the erosion control system. So some quality management system certificate obtained through the ISO is concerned. Okay, it seems I have a little bit problem, but you remind me if you can't see it. Okay. And locally is concerned, we have JKR approval for all our products available in the market. And this is important. So all this research, all this development, product development is concerned, make us not only a manufacturer or a distributor selling the geosynthetic material only. It is also make us to provide us a standing in the market as the practical solution provider. And then most importantly, we know how to get them built, how to get all these reinforced soil structure built based on the experience and the technology available on us. So in today's concern, we're going to discuss some introduction, what is the reinforced soil structures about, and we'll talk about some design parameters of the geogrid reinforcement. And we will go to see how to do the design of the reinforced soil structure, just a little bit, not really into a detail of it. And we will go into a more interesting part, which is a case history in Malaysia. We will look at some of the structures we have been building using the geogrid reinforced soil system. And followed by a Q&A session. I will let you ask me a question first, then later on, as requested by Dr. Chimeng, I will provide some question to ask you back, so you answer back for me, see whether how much you can understand from my presentation. Okay, so in designing of a reinforced soil structure concern, there are a lot of the questions you might ask. And for example, like what is reinforced soil structures? So when we talk about, for people who first heard about these reinforced soil structures, in fact, it is not something new. As we said that Dr. Brian Mercer founded the what they call the Netlon and following by Tensar since 1950. And in Malaysia is concerned, we start using the geogrid reinforcement to build the structures in 1986. So it is probably like 34 years ago in Kuching, Sarawak. So this is a near vertical structure using the geogrid without any hard facing. So it's just using the wrap around technique, as you can see in this cross section. So initially, this structure is used as a temporary ramp, but later on they found that the performance is good, so they maintained it for a longer time. So the facing is tough, as you can see in this picture. It's a very, very old picture. So in this picture is concerned, it shows the three types of the geogrid in general. One is the uniaxial geogrid, which we use it to reinforce the retaining structures like slope, walls, and so on. The other two is the biaxial and triaxial geogrid, which we usually use it to stabilize the subgrade or ground. Okay, we in the subgrade stabilization application, but we do use this type of geogrid as a secondary geogrid in the slope construction as well to control the localized stability in between the main reinforcement. So in general is concerned, reinforced soil structure actually is a stabilization of earth field using the polymer geogrids, which they lay the geogrid layer by layer at certain interval, and then put the soil compact, another layer of geogrid, put the soil compact, another layer of geogrid, and to construct it up to the platform level that we require. So we know that when we want to fill up a platform, at the edge of the platform, maybe we say that somewhere near the boundary, we have to either form a slope or a vertical structure like retaining wall. In conventional way, people like to use like RC retaining wall, for example. So if you want to form a slope, if you have space, maybe you form something like a very gentle slope. Usually engineer will call it 1:2 slope, which means 1 meter height and 2 meter horizontal distance. So this is a gentle slope, roughly about 26 or 27 degrees. And that is due to the reason of friction angle of the natural compacted soil is around like 28 to 30 degrees. So what if we want to form a steeper slope, like what we show here in this diagram? Yes, you can still do it, but when an engineer put this cross-section in a design analysis program is concerned to run to check what is the factor of safety for the critical slip circles or slip surface, for example. So you will find that when the slope goes steeper and steeper, the factor of safety is dropping. Okay, so when it drops until that less than 1, then this structure is unsafe to build. So what you need to do is one of the technique is using the geogrid reinforcement. So we lay the geogrid reinforcement layers by layer at certain vertical spacing and make sure that it is going beyond the critical surface. So when this active zone is tend to slack down, the geogrid is able to hold it back. In other words, it converts the whole piece of the material over here to become a composite material. We call it a reinforced soil where it has a better friction angle in general. Okay, so this is the reinforced soil concept. So what type of structure we can use using this technique or system? So as you can see in the picture, we can use it to construct a slope system. We can use it to construct a near vertical system like retaining wall systems. Or sometimes with the combination of both, then we can optimize both the cost and the land use purpose, for example. So it depends on the requirement. So in slope system is concerned, usually it will divide into 2 types in terms of the construction technique. One type is slope, where it is up to 45 degrees. You still need to use the geogrid to stabilize it. And this doesn't require, in our system is concerned, this doesn't require to have a wraparound facing, okay? If you want to build something steeper than 45, but it's not vertical, and you don't want to use a concrete facing like a keystone block or whatsoever, then you can do it with the wraparound facing at steeper angle like 70 degrees. So we will see through it, these 2 systems through some photographs later. So these are some of the facing that we require for slope gentler than 45 degree slope. Then we do not require any wraparound facing. After we construct it, then probably trim back, put the turfing. All right. But if it's for the slope steeper than 45 degrees, then either we use a wraparound technique with some backworks or formwork at the facing of the slope, where to facilitate us to allow us to do the compaction well on the facing, or the other way is to use a steel mesh. So this is a photo showing the 45-degree slope constructed using the non-wrap-around facing. So the geogrid laid, this is the main reinforcement geogrid. It's a uniaxial geogrid. Okay, we lay it this way horizontally at certain spacing, and you can see that in between all these main reinforcement, there's a shorter geogrid in between. So we use this one, okay, probably like 1 meter length, for example, to control the localized stability in between the main reinforcement. If the main reinforcement have a bigger spacing, like for example 1 meter, then we require a secondary geogrid. Then we can have the facing by just putting the vegetation turfing, close turfing, for example. So it look very natural in overall. The other way, if we want to maximize the land use a little bit, you make the slope steeper, for example, like up to 70 degrees. Then you have the geogrid to wrap around, and all these earth bag will be put in front of the facing to allow us to do the compaction. Otherwise, it is not stable and it's unsafe to compact the earth over here, and you can't have a very good compaction. So this earth bag is to provide some confinement as well for the soil when we do the compaction on top of it. So it's wrapped around, then it will connect to the upper layer of geogrid using a Bodkin joint this way. Okay, so it will connect through, so on until you reach the finished level. The other one is the retaining wall. So locally it's concerned, usually we'll use a segmental block called keystone to construct these near vertical retaining structures. Okay. If you don't want to have a keystone facing, the other way you can have a gabion facing, or we call it a rock face facing. There are some other facing available in the market as well. So these are two general facing available in the market. Okay. So now we have an idea roughly what is reinforced soil structure, what type of reinforced soil structures. And if we say we want to go to design it, and we would like to know that what is the reinforcement required for it, and how strong, what is the strength that we require? Is it durable in the soil when we put in the geogrid, and how long it will last? So these are some of the questions we will ask during the design, and it is important that we have to understand the design parameters for the reinforcement that we use in our design. So in general, it's concerned when we put up a reinforced soil structure like this, internally is concerned for the geogrid, it will have few possible failure mechanisms. We need to understand the behavior first. For example, if this piece of the soil is going to push up or is going to fill for certain reason, then you will have maybe a pull-out failure, something like this, meaning that the geogrid that we put in is not long enough, so the whole thing will pull out, or it will have the rupture failure. Okay, you have the rupture of the geogrid, meaning that the geogrid that we put in is not strong enough. Okay, and the other one is the connection failure. So these are some of the attention you need to put in on the connection between the facing blocks and the geogrid. Okay, so there are different type of geogrid available in the market. For example, as what we can see in this picture is a geogrid like this, which we call it a HDPE geogrid using a punch and drawn manufacturing technique. Okay, and there are some other geogrid available in the market as well. Like for example, we have this kind of polyester geogrid. Okay, it look very flexible, and the joint can move. Or we have this type of welded joint geogrids, or this kind of woven geotextiles, and so on. There are different products, but today we will focus in this HDPE geogrid because this is something I would like you to know more for today. So this is a series of HDPE geogrid manufactured by us, by Tensar, and we can see in this picture is concerned, this is the main machine direction, which is the main ribs, and this is a transverse bar. It helps to distribute the load to the main ribs of the geogrid when there's a load applied on it. Okay, so it's a uniaxial geogrid in this way, main direction, main machine direction. And to understand the what we call the creep rupture strength of the geogrid, one of the good way is to carry out long-term sustained load test. We call it a creep test to understand the behavior of the geogrid, the elongation, and over the load and over times. Okay, and like it or not, this is the material, polymer material, HDPE, or people in general call it plastic, and it is quite sensitive to temperature. So what we call the strength changes over the temperature. So we need to understand also how it behaves. What is the creep strength at different temperatures? So we carry out all these creep rupture strength tests in the different temperatures as well, from 10 degrees to 50 degrees Celsius. And all this will be recorded in our specification sheet. And it is also important that all these result or parameters is concerned, is being studied, is being recorded and accepted by the independent authority, like in this case is the BBA, British Board of Agreement certificate. So it call it as a approval, inspection, testing certifications. Okay, so they go through what manufacturer is doing. They go through whether this data is something real, something useful and correct to be used. And from this data is concerned, it will provide you a short-term tensile strength as well as the long-term creep rupture strength for the 130 years and the 60 years strength, for example. All right. So you will get all this then through some techniques of extrapolation of the result in the lab. Just now we see in the pictures, then they will get some result on this. And this is the manufacturer model specification. So one part is concerned over here when they talk about the long-term creep rupture strength. It will give you that what is the strength of the geogrid at what kind of temperatures and for the design life of 120 years. And this 120 years is a requirement by the code like British standard. And in the extrapolation of the result is concerned, we need to have a real-time minimum of 100,000 hours of the continuous creep testing, meaning that the one we see in the picture where they hang the load over the geogrid, it has to be continuously carried out for a minimum of 100,000 hours to get a more accurate creep rupture strength in our design. Okay, these are some others in the specification, like the junction efficiency and so on. If that is one of your concern for those wraparound facing using the blocking joint. So upon getting all those parameters, and we would like to carry out the design, and what are the numbers? Is the numbers just now recorded in the this specification sheet allowed to use? Not yet. We still have to consider, like for example, some partial factors that we need to apply to get our what we call the long-term design strength. This is the design strength. So we use a creep rupture strength and divide by the partial factor, for example, as recommended, the extrapolation factor, the site damage factor, and the environmental factor. Later we'll go through these two a little bit. So we'll first look at what is site installation damage factor. It is something like we put the geogrid and we compact with the soil, and how this soil will actually damage the grid, how much it will reduce the strength. So for us, it's concerned, we have carried out a full. Okay, can you still see the slide? Okay, yeah. So for us concerned, we carry out a full-scale site damage trials, as you can see in the pictures. We put in different types of geogrid, and then we put in different grade of backfill material. We compact it, we construct it as in the usual way, and then slowly dig it out after some time and cut a piece of geogrid, send back to the lab and do the testing. And this will check against the site damage factors on different type of field grading, meaning that we have sand, we have something like in these pictures like kashuran types of material, and how much it caused the damage to the geogrid. Then from there, we develop what is the site damage factor against the size of the particle field material. And we also need to understand for certain site, for example, we use it in the landfill area or some area which quite sensitive in terms of some chemical attacks, and how our geogrid that we put in will behave, or it can react over all these attacks. So lucky is that HDPE is concerned is the one of the polymer material which is quite inert to all these acid and alkalis kind of material that we possibly found in soil. But still, there's a limit to it. Later in, I will extract the table from the BBA certificate to let you see the numbers. So this is a table for the installation damage factor. For example, we have a very fine material of the particle size 0.65 mm to 110 mm. If we take, for example, RE540 is concerned, if the field material is very fine, there's no damage to the geogrid, so the partial factor is 1. But if the field material is a coarser material, rocks or kashuran material, then certain partial factor need to be applied in calculating the long-term design strength. So we have to know what is the pH. For normal backfill soil, no concern, because like we said, that pH in the range of 4 to 12.5, there's no problem at all. So the partial factor is 1. There's no reduction in the design strength. But if we have something very acidic, for example, the pH value 2 to 4, then it's a little bit concern over it, then we need to reduce the strength a little bit. Well, like I say, not only this type of geogrid available in the market. As an engineer is concerned, you can do the design, you can carry out your design or build your walls using different kinds of geosynthetic material. This is one of the options, which is the most popular one. Or you can use kind of geogrid, as you can see in the picture, which formed by a polymer called polyesters. Okay, so this polyester geogrid is concerned, same thing. When we're concerned about the long-term design strength, then we have to study carefully what are the partial factors that we need to apply, especially like polyester geogrid. It concerns over the hydrolysis in a very high pH or high temperatures. You will have the huge reduction in terms of its design strength. So as an engineer, we have to apply it accordingly and correctly in our design. So that is a little bit on the parameters, how we can get into the right design strength. So now, after getting all this, we need to carry out the design, how to do it. Of course, today I'm not going to go through with you the detailed formulas. That one I let Dr. Chimeng to handle it for you in the class. But I'm going to tell you in general how we do it. So over here is concerned, we are doing it using the design software. So these are different kind of design software to take care, like for walls and slope, we're using the Tensar soil, and stability analysis is concerned, we're using our software called Tensar Slope by the Bishop simplified method. Okay. So when we carry out the design internally, we want to make sure, like we see in the earlier slide, we don't want to have a pull-out failure. So we want to make sure that the geogrid is long enough. We don't want to have this rupture failure. So we want to make sure that the geogrid is able to resist the lateral pressure applied on it. Okay, so the geogrid has to be strong enough. So externally wise, we want to make sure that we don't have the sliding failure. When the lateral pressure push the wall, it won't slide out. It maintains in place. It doesn't have the overturning failure. Okay, so need to check the base properly. And you don't have the bearing or tilting failure, so need to check the bearing capacity of the ground, which is supporting your wall below it. And this is also one of the important one. We don't want to have a slope failure. So we'll be like in this software or design process is concerned. First, we will design the internal stability of the wall. Make sure there's no pull out, make sure there's no rupture, failure. When all this done, then we need to check the overall stability, like bearings, slip circle. Then some it can be helped by this software like Tensar slope, or maybe the one you're familiar is slope W, for example. Okay. So this is a typical section of the modular block wall, or we use a keystone wall. So over here, this is a facing. Facing should be the keystones, okay? And if the ground is competent where there's no further treatment is required, then usually what we do is that we will provide a mass concrete pad, which is to provide a flat level for us to put up the precast segmental block. And the geogrid will be installed layer by layer. So maybe you will ask, what is the length of the geogrid that we need to predetermine or we need to design? So it will the ratio, we call it the L over H ratio is concerned. It will provided by the different codes, will provide you a different range, but usually it range around, for starting point is concerned, it range around 60% to 70%. So if we have a wall of 5 meters, then the geogrid length that we need to put in minimum is 3 meters. This is 60%. If let's say if you go for 70%, then it will be 3.5 meters. Okay, for flat top structures. If you have a slope on top, then different story. We need to calculate what is the effective height, and then and so on. Okay. And in BS 8006 is concerned, these are some of the structures arrangement that we can build using the geogrid reinforcement. One of the full height wall. This is a normal way of the normal wall, I would say, and this is the wall with the slope on top. And there are some they call it step wall. Maybe the bearing is weak, so we need to lengthen the geogrid at the base. And the other one, trapezoidal wall. If you have you are constructing a wall at the very stable slope, like a rock slope, for example, you can actually reduce excavation by doing the stepping in this way. We form a trapezoidal wall shape, back-to-back wall for the highway, bridge abutment construction, and so on. Okay, so we can refer to the codes. Then the code will tell us what is the length of the geogrid recommended. And as an engineer, we can pre-design it, and we design it accordingly and check the stability. So nowadays, we are quite lucky that there are a lot of the design software available in the market. Okay, for example, the one that we are using is actually quite user-friendly, where this is the orientation of the wall. We just need to tell the software what is the height of the wall that we want to design. Is there any slope on top of it? If there is, like for example, 1 meter, what is the angle of the slope on top of it? And what is the embedment that we want to put in? But this embedment doesn't, usually we will neglect the passive resistance. Okay, there for some reason I'll explain it later. And what's the length of the geogrid that we want to put in? In this case, we're using 70%. Okay, so by putting all this scripting, filling in the soil parameters, and this probably we can obtain through the borehole results and the lab testing result, for example. Okay, then we can just clicking the button, arrange the geogrid, at what kind of spacing, what type of geogrid, and so on. Then we can just, by clicking few buttons, then it can calculate for us what is the internal stability, what is the external stability of the wall. Okay, so for the embedment is concerned, usually there are some guidelines provided by the code, for example, like BS 8006 is concerned. But there are also sometimes we need to modify it, maybe to become deeper. For example, if you have a drain just next to you, so you don't want to introduce a lot of lateral pressure to the drain, then usually we have to deepen it down. So it depends on the design, depends on our consideration as an engineer. So this is something we have to decide at this stage. Okay, so after clicking run, then the program will tell us, oh, at which level, you see a lot of lines. So if it's about technique method, it's 2-part which is concerned. So usually it will the analysis will cut the line here, and then to analyze what is the resistance force, what is the acting force on this structure. Then I'll cut many lines to check that which angle is not okay, like was and so on. Okay, so we just need to modify until we get the satisfying results. So upon finish that part, then if the structure is like, in this case, if founding on the slope is concerned, where stability is a big concern to you, then we have to check what is the stability of the structures. Okay, so we carry out slip circle and so on. So there are some modifications which will depend on the requirement of the factor of safety and what kind of, like in this case, is using the BS code. So we just have to make it more than one, because BS code is applying those partial factor. Okay, so if you're using the Bishop simplified method, then it depends, like we need the factor of safety of 1.5, then we have to find some way to achieve it. Okay. So after getting all this design done, then we start preparing so-called construction drawings. So you did some details we provided, like what is the size of the layering pad, and what is the arrangements of the geogrid, what kind of fill that we want to fill inside. Is there any filter layers that aggregate in between the blocks and the fill layers? This is something that we need to put in our drawing, so that our colleagues or our men on site, they can do it accordingly. So as we can see in this cross section is concerned, there are few elements in forming this Tensar keystone retaining wall. So one is the layering pad, as I explained earlier. So after putting, maybe it will have some steps if the platform is not flat. Okay. Then we will stack up the keystone block, lay the geogrid, backfill, another layer of geogrid, backfill. So this, we call it an aggregate layer is concerned. It acts as a drainage as well as a filter, because what we fill in here is something quite fine, sand or some suitable fill. So this block, there are some gap in between. We don't want those fine material being seeped out or go through the gap. So we put in 20 mm size down aggregate as a filter, as well as for the drainage purpose. So there are a lot of details we can play around with engineering sound. Okay. So now I have gone through some little bit theories, design parameters, and then how to get it done, anything that we need to concern during the design. So now we will go through the interesting part, case history for the reinforced soil structures that we built in Malaysia. So the first one is the geogrid reinforced soil slope, and the wall is a combination of both systems. So this is a project located in Terengganu. I think it's called Krop. So it's a slope failure next to an existing water tank. It just finished building, and luckily no water filled up yet. So the slope has actually collapsed. And this wall that you can see in front of this picture, initially it was at the location of somewhere here. Okay. So this is a layout plan, and the slope failure is somewhere over here. So when we went up to the platform and we look at it, is concerned, even the apron has a severe settlement over here, and the slope failure is somewhere over here. Okay, so if you look at these overall pictures, so this failure, after we study, there are some few possible failure factors that causing the failure. Maybe later we can go through a little bit. So we can see that the slope is really moved towards it, and there are some drainage, there are some cracks, gullies on the slope, showing a very unstable sign of the slope. Okay, and you see people build the drain with the U-turn like this, and it's quite a shallow drain. Multiple tension cracks. Okay. Some pictures left and right showing the condition at the bottom, waterlogged in certain area. So there might be some you might have some doubt on the foundation of these substructures. Okay. So upon visiting the site and getting some information, so we found that very poor surface drainage system in the first stage of the construction. As you can see, the U-turn drain very shallow, so we foresee that the overflow of the surface runoff during rain, so it will wash the slope, it cause seepage and so on. Okay, and very poor maintenance of the slope because we don't see that the grass is growing and so on, and poor foundation on the slope as well as the existing RC wall. So this is the proposal that we put out. We as much as possible, we provide back the platform on top of the slope, which is next to this existing water tank. And we improve the base by doing the removal and the replacement after determining the soft layer at the bottom. And we have a 3 meters keystone wall built below it, so that we can have the slope found on the existing alignment in the earlier stage. And then we make some, I would say, in between steep and gentle slope. It's not that gentle, but it's something like 30 over degrees, and 4 slope on top. Okay. So the proposed slope repair scheme involve the remove and the replacement at the slope toe as a ground improvement, and remove the loose material and the collapsed RC wall. All the collapsed material, including RC wall, loose soil, it will be excavated away. Then construct the keystone wall as well as the geogrid reinforced slope to improve the overall stability of the slope. So more importantly, improve and construct a proper surface drainage as well as the subsoil drainage, so that we can lower the water table and drain away the subsoil water as much as possible and as quick as possible, using the sand blanket and sand column kind of thing. So in this section is concerned replacement, and you see this legend, we fill up the sand for the wall, followed by the sand column, and we will terminate it before the second slope. Then the same idea again. Okay, we have sand layers and then the sand column, sand layers, sand column. So all these sand layers and sand column is to facilitate, if there's any water at this level, it will go into the column and it will be able to drain up to the berm drain and discharge away from the slope. Okay, so same thing over here. And I would like to highlight that, remember, if you do some details like this, always do not connect your drainage layers or columns all the way up to the top platform. Okay, we terminate at each slope so that it is able to drain away the water from the slope as quick as possible. Okay. All right, so some SI being carried out at the different level, and we gather the information as well as the Macintosh prop, so that this will help us to determine the soft layer and how much we need to excavate away. And these are some of the results that we obtain, of course, doing the analysis. Okay. In this case is concerned, the requirement is that for us to achieve is a minimum factor of safety 1.5. So we have to make sure it's all done. And this is some surcharge load that we put on top, including some temporary surcharge as well as the loading from the water tank above it, because that water tank is not supported on pile, it's on rough, and the other end may be on pile. So this is the failure profile of the slope. It's quite gentle, isn't it? But it's because of the failure, it covered up here and there already. So I'm going to explain you the construction sequence, how we carry out. Usually, we will carry out this type of repair, start from the bottom. Okay, start from bottom and then build up. But for this case is concerned, we have a concern that there are some loose soil next to this water tank, tall water tank, and we worry that if we excavate and cause some movement on top, movement of the soil on top, then we worry that this water tank might move as well. So we decided to first start with the repair or strengthening works on the platform next to this water tank. By excavating now, move away the loose soil, then we put in the geogrid, we extend it a little bit outside so that we can connect the geogrid to form the slope in front of it later. Okay, so we first complete this part, so the top is all compacted and firm, and then we excavate to remove the loose material partially at the top, fully at the bottom here, to carry out the replacement. Okay, replacement, construct the wall, layers of geogrid being installed, followed by the slope. We excavate again to remove away the loose material at the top, then construct the toe wall for the second slope, follow the same thing, move away again, construct the third slope, and the fourth slope is a small slope where we put in the geogrid and connect it back over here. Okay, and of course followed by some drainage system like berm drains, toe drains, cascade drain, and whatsoever. And upon completion, close turfing on the surface of the slope, make sure it's all right. So these are some of the construction pictures that I would like to show you. Follow the construction sequence. Okay, so this is a top platform covered to provide the temporary protection to prevent the water seeping into the soil. Okay, covered. So we first excavate in a small section to improve the top platform. Small section. Okay, so upon compact it up, this is some extra geogrid we allow for the blocking joint later to connect the geogrid for the repair slope in front of it. Finish, continue with another section, continue with another section. So we carry out in a smaller section to ensure the temporary stability of the slope is being taken care. So removing of the root soil all the way down, and then do the replacement at the bottom, construct the retaining walls by using geogrid and followed by the slope on top. And this is the end products. As you can see that, of course, over here we can't see clearly. There are berm drain at the berm level here. It will discharge away through this cascade drain, and from here it will be discharged away through the toe drain. So the whole drainage system, the surface drainage system, is complete. Okay, so we reduce the water, or we discharge the water as fast as possible away from the slope through all these surface drainage system. Okay, so that is the combination of the what we call the wall and slope construction techniques. So another one I would like to discuss with you is the steep slope construction, where we use it to repair the Kuantan-Kerteh railway line. It's a cut slope failures. This is a slope failure profile. So maybe by looking at the line, it doesn't look that bad, but if you look at it is concerned, it is quite critical at the site. And we can see that the railway line is pretty close to where the slope failure is. So if you look at it, now you can see the problem by quite a lot. So KTM is concerned cannot afford to close the railway line. They still have to allow the traffic pass through. So in view of this critical situation, they understand that the slope repair work has to carry out immediately. All right. So it is not strange to see that the slope fail near to the transport line, like the roads, like the railway. Okay, so like for railway is concerned, if it happened, it can cause a big problem like we see in the picture. This is not the same site as we did the repair, but if this slope failure hit the train at KM 208 of the Krambit-Kuala Lipis Railway back to 2009, okay, it can cause a big disaster, and a lot of efforts to clear and a lot of the lost. So in our repair scheme is concerned, since this is a cut slope, okay, by carrying out the test, determine the soft layer and so on, what we propose is to build a stable steep slope as a bottom, okay, and then we reprofile the slope on top of it, including some backfilling of the slope, gentle slope 1 to 1.7, some gentle cut of slope on top of it, and provide a very good drainage, okay, surface drainage to drain away the water. So the construction begins with extracting the existing ship pile, Of course, before that, they have already removed some loose material as well. And then this one using the steel mesh facing, where the uniaxial geogrid will actually form and connect at this, what you call, the steel mesh, and layers by layers to build up. Okay, so we can see the blocking joints over here and the facing. Okay, and while it is under construction, they also turf it in the midway and followed by all these berm drains and cascaded drain construction above it. So it was completed in 2005 on May. Then this is in 2 years later after the completion. We can see grass grow. So you don't really, people who don't aware of the history of this slope, they don't really know that the slope has been repaired before, so it looks orange. Okay, this is 1 month after the completion, so we can see from one side of it, and this is overall view. The structure is somewhere here after some years, right? So the other one I would like to discuss is that the hybrid construction method. So this time we are using the reinforced soil slope and soil nulling method. For example, we have a cut slope failures like this. Okay, this happened in Fraser's Hill to a very famous resort or hotel, I would say, built in 1937, smokehouse. So these are some of the information of the failures. So the challenge of this slope repair is concerned, the work is concerned, we have an old building just, or maybe it's already inside the slope failure. So we can't do the excavations a lot to allow the geogrid to be installed into here if it's necessary. Okay. So this is a condition of the failures. They will cover up everything with tarpaulin sheet to provide a temporary protections. So one of the reasons is the hotel owner, they have extended the hotel backyard, okay, by their way, and a lot of weight has been putting up on the existing slope before the failure. Then, as well as there are a lot of the water pipings is being connected without any planning, and they just discharge it. People say suka hati towards the slope. So it caused the failures in the end. So what we have proposed is using the reinforced soil system with a combination of soil nulling. Okay. So two reinforced soil slope is formed, and there's one cascade drain will be provided in the center, connect to the berm drain and discharge through a rock toe above it to reduce the water velocity at the bottom here. And this is a cross section. Okay, we have a building here, and because if you look at the slope profile is concerned, it doesn't end here. It is actually all the way down few hundred meters to the bottom. Okay, so we can't afford to have a gentle slope, and you will chase along the slope, and you need to build very, very far away, and it's not economical. So what we study and propose is to use a combination of both the geogrid and the soil nulling. And the building is over here. We can't afford to excavate further because we cannot bring down this building. So only short geogrid is allowed to install over here to make sure that this slope is stable by itself. And we provide some micropile so that this reinforced slope, the load of this reinforced slope is able to transfer to a better ground below it without transferring further onto the slope. And for the soil nulling behind this is concerned is to provide a stability improvement or enhancement for a deeper circle at this line. Okay, so we give them back the platform. And this is the overall what we call the repair scheme that we propose. So we start by removing the tarpaulin sheet, and we can see that behind the scene or below the tarpaulin sheet, there are a lot of rubbishes. There are a lot of rubbish, construction waste, collapsed material, rubbish here and there. And the challenge is the access road is very narrow. It's very difficult to carry out the works. Everything have to do it slowly, and this is up on the hill. The material also very difficult to to reach our site. So we will have to control the imported material as little as possible. So the construction works starting by removing the loose material at the platform here, and then we install the micropiles. Okay, install the micropiles. After complete everything, construct the foundation slab, and then it followed by the soil nailing construction. Then we carry out the pull-out test to see whether the design strength has been achieved. Then we continue with the installation of the keystone block, followed by the geogrid behind it. So what we can see here is concerned. This is the soil nailing being installed, and at a certain level, we are connecting the geogrids using the GI pipe, forming the bocking joint, then hook and place behind the plate of the soil nail. So this allows us, the geogrid, to transfer the load to the soil nail behind it, and it can go further inside, right, as a type of enhancement as well. Okay. So in slope construction is concerned, always there's a concern that what we call the stability on the surface. We want to have a slope surface to be compacted as much as possible. And during this construction is concerned, you can see that after we compact everything, the surface seems loose. But the right method is we carry out the slope construction by overfill a little bit in front of the slope profile that we want to form. Okay, then compact it up to a certain level, we trim it. So after trimming this part is what we see in the picture. It's quite loose. After we trim it, because we have do the compaction layers by layer, and this part is concerned, it is well compacted surface on the slope. So it is something very simple, but it's a very good practice to carry out on site to ensure that our slope surface is properly compacted. So after you trim it, you get the result like this as compared to the untrimmed section above it. Okay, so you trim it, you get something very well compacted. And of course, if you finish work, there's some temporary protection has to be done. Importantly, after you trim it, then you provide turfing. Okay, and followed by the drain construction, cascade drain, so that it discharges water to the bottom. And this is the almost complete stage of it. So this is a picture, shows us the before and after. So this is a before condition, after we have put up the slope with the reinforcement inside actually, then with some soil nailing over here installed. Okay, so this part is concerned. It looks like something like this. So we give them back the platform, the walkway over here. And we rebuild the slab within the building itself. And these are some saddle bars for them to build, for the owner to build the column to support back the structures above it. So temporary structure is provided. Then we provide a very good access back to them. So this will allow them to carry out the maintenance work of the slope easily. For example, as compared to previously, full of turf, nobody is able to go in to carry out the maintenance of the slope. Okay. And the drain, this is an interceptor drain that we provide right after the gutters below the building, so it can collect the water as much as possible without rushing to the slope. And whatever water come out, water pipe or whatever, it come out from the building is able to cut off by this interceptor drain and then drain away. Okay, drain away somewhere here. The dome drains, cascade drain, as well as a staircase for them to carry out the maintenance in the future. And this walk path is provided a little bit nicer because Fraser's Hill is also one of the spots at certain season people will go and go for the bird watching. Okay, I don't watch at birds, but some people like it. Okay, so we provide a very good walkway, and this is the overall completion of the slope without disturbing the building, and we provide back the stable slope, give them the platform, improve all the drainage system as well as the slope stability. Well, just now what we have seen is not a very huge structures, but in fact this geogrid reinforced soil structure can be big, can build something big. In Pembrokeshire, Sarawak, Pembrokeshire Highway in Sarawak is concerned, one of the reinforced soil structure that we built is for the road embankment up to 30-meter high. So you look at the cross section is concerned, every berm is about 5 meters, 1, 2, 3, 4, 5, 6. So we have overall around 30 meters high in total. Okay, so this is some design cross section and some detail. And it's still under construction today, still ongoing. This is a closer view of it. Okay. And for the vertical structure is concerned, if you have money, of course, you can build it huge as well. Of course, in Malaysia, we don't do it that big, but this is one of the huge structures that was built in Middle East Highway. I think it's in Dubai. 3 tiers wall consists of 20 meters, 20 meters, 20 meters of wall at each tier. So total 60 meters in completion. So this is the size of the machineries, compactors and so on, trucks, lorries at the bottom, and this is the size of the structures. So it can be done. So in this picture is showing that they're building a road crossing using the wall over a valley. So over here, they allow some covered for the water to go through in the future, big covered. So in this case, they afford, because in Middle East is concerned, this is somewhere far away and they don't have the concrete plant to build the elevated structure or whatsoever. And those good backfill material is actually just next to them. So they can just do the excavation here and there, get the good backfill material, and then backfill, use it as a wall fill to fill the structures up. So it achieves both the economical way and the technical way. Okay, this is the other side of the completion of the wall. Okay, so even if we go back a few thousand years earlier, the reinforced soil structure the concept is not new. Our Datuk Nenek at that time is already know how to do it. And what they do, they use a fiber material, also embed it or lay it within the soil layers by layers, but of course thinner layer, to build a structure in few thousand years back, the Great Wall of China. So that is a bit of my sharing session. So I will open the floor for the Q&A session. You have, and we can discuss about it. It's about 3 o'clock. All right.
All right. Thank you very much, Jim Boon, for a very interesting presentation there. Right. So now we are open for questions. Any questions from the audience? And just turn on your mic, turn on your video, show us who you are. Anything?
Yep. Because if you don't ask the question now, then later on there are questions for you.
Students especially, perhaps you should ask some questions. Mr. Chan has shared with us some very interesting case studies, as you can see, especially in terms of the construction procedures that we don't learn in textbook actually. For example, over compacting the slopes and then cut it down so you have really compacted surfacing. Yep. And the trimming part of things, and how rehabilitation work can be carried out on a failing slope, like the one that involves the water tank. So imagine if it's carried out before stabilizing the part of the slope, the top of the slope that's near the water tank platform, and further failing may take place, and that would jeopardize the people working around there. So I think students come on, some of you, I mean, your project would have involved the slope stabilization using materials similar to Geogrids, like what Mr. Chan has shared with us. So perhaps you want to ask a question?
Yep.
Cairo mana?
Ada.
Yep.
Mana soalannya?
It is crystal clear.
Crystal clear. Thank you very much. I think one good point that Dr. Chiming or Dr. Chan has mentioned just now is there are a lot of the things that in the construction or the civil engineering is concerned, we do not learn it during the university time. I'm not talking about the calculation part or the knowledge part. Certainly you can get all those knowledge from the university part. It's something like the practicality of the structures of our design. So as a design and build specialist contractor like me is concerned, we have the advantage because we have a design technical team in the office, and then we have a construction team, very experienced construction team at the site. So usually our design, we will have a good discussion with our construction team to see that whether it is practical to carry out, is there any way to improve it, and so on. So what I would like to tell to the students is concerned, you are the civil engineer to be in the future. Okay, maybe in 5 years or 10 years down the road, you probably my clients or my customer or my consultant. But always keep in mind that we always have to respect the construction team personnel. When we carry out the design, put more effort to discuss with them whether it is practical to be done at site. In terms of the detailing, in terms of the construction sequence. Okay, so from there, if you learn it through this path, then from there you will find that after this, you will have a very practical solution towards the what we call the construction later. So this is one part I would like to highlight to the student. Don't always just look at the piece of the paper, but go to the site, learn, listen, visual inspect yourself, and then convince yourself, okay, and discuss, exchange of information, and discuss with the site person.
Yeah, that's a very valid point that Jimo has made there. It's about design on paper is almost always perfect, picturesque and beautiful. Yeah, but on site it may not be that way. And the people on site, those are the people who are very well versed, and they will know that whether something that we put on paper is feasible, practical, or even safe at all to carry out on site, right?
Yeah. Yeah. Okay. So okay, you have my contacts over here. If you can't think about the question now, probably you can email to me, to my direct email, if you have the questions later. So I will try as much as possible to reply you in the email, hopefully to give you a good answer. So now, if Dr. Jimen, can we go for the question session for them?
Sure, they're waiting for it.
Okay. Okay. So I have some questions. I just give all the 5 questions, and probably we will have 10 minutes for all of them to come back to us, because it's not like in the classroom we cannot do it in a group. So everyone just refer to these questions, write down your answer, and later on for every question we pick one student per question to answer the question. Is it okay, Dr. Chiming?
Yeah, sure. That'd be fun.
So 10 minutes countdown. We'll come back at 3:20.
Yeah, sure.
Okay.
So everyone can either you take a break or you start answering the question for the students. And I would strongly recommend that start looking at the questions and looking at the answers now. Okay, we come back in 10 minutes time. All right.
Yeah. Okay.
All right. Yep. Students, anyone ready to answer the questions? Anyone?
Yeah, maybe we can start with Cairo.
Yeah, we can start with Cairo. Yes, Cairo, are you there?
Went somewhere else.
Cairo.
Yeah, for the first student to answer the question, you can choose any questions to answer. You don't have to follow the sequence. Carol, can we hear from you?
Or friends of Cairo. Come on, students.
Okay.
Still looking for the answer.
Yeah.
Hello.
No, I still looking for the answer.
Okay.
Mr. Chan, I would like to answer the first question.
Oh, okay. All right.
My name is Tasha, and you asked what is the meaning of Geogrid, right? So in my opinion, it is a product used to stabilize the soil by reinforcing the soil. And this product comes in 3 types, and you were focusing on uniaxial, but there are also biaxial and triaxial.
Yeah, biaxial and triaxial is more for the subgrid stabilization, but sometimes they also use as a secondary geogrid for the reinforced soil slope.
I see.
Yeah. Okay.
Thank you.
Thank you.
That is something, if you recall, Jimun shared with us earlier on, the in between the main reinforcement elements, if they are far apart, like 1 meter apart, then in between we could put in the secondary ones. All right, Tasha, got that?
Yeah.
Yes, doctor. Thank you.
Thank you. Okay, good.
Okay, next question. Come on, students. Don't be shy.
Yeah. Yeah, hi. Hey, mute again.
Iqmal mana? Iqmal? Okay, maybe we pick a girl this time around. Let's see.
Yeah.
Is it for the question number 2?
You can answer anyone you like.
Yeah, you can answer any.
For the question number 2, this is types of reinforced soil structure. I think the answer is slope system something. Is it?
Yeah. Okay, then so on. And what else? We need types. Yeah.
Wall system, combination structures, a wide range of literature available.
Oh, the fourth one is not. The fourth one is just to say that they are discussing about these three. So can you tell us what is the combination system?
Combination system.
Yeah.
Um,
Slope system
I
correct. Wall system correct. Combination system is correct also. But what is combination system?
is it both slope and wall system?
Yeah. Yeah. Okay. All right. Good. Very good. So question number 2 answered.
All right.
Very good.
Right, guys, as you can see, Dr. Asana is taking note. Those who have volunteered to answer here, being proactive, you are given bonus marks, all right?
Oh yeah.
So come on. There's no right, there's no wrong. It's a discussion. Come on.
Yeah.
It's for number 2, right?
Number 2. Just now was
Yeah.
number 2. Yes. And
The 3 types of reinforced soil structure is uniaxial, biaxial, and triaxial.
oh no, that's not correct.
That's not.
We are talking about the reinforced soil. What are the types of the reinforced soil structure, not the geogrid reinforcement?
I'll go through the slides again. Come on.
Yeah. The types of the reinforced soil structure has been answered by your friend. So question number 2 is already answered. In general, there are 3 types of reinforced soil structure can be done. Slope system, wall system, or the combination of both. So meaning that we have walls, we have slope together. So question number 2 has been answered, is already answered.
Right, students, you got the slides, right? Has been shared with you, so you can look through them if you cannot quite recall. All right?
Yeah, I couldn't find the 65 slope.
Yeah, it's not mentioned, but it is something that's to test your understanding. So if we have to construct a 65-degree slope, what construction technique can you use or in the design? You can check back the slope system, the one at the earlier few slides of the slope. There's a table, the chart showing that what are the techniques you can use.
Oh wait.
Yeah.
This is Dick one, right?
Yeah,
Cairo again. Okay, fine. This is about the slope. 65 degrees is a very steep slope. It's almost vertical, going towards vertical. So what kind of system can we use? That's the thing.
Yeah, I think Cairo certainly need to answer one question, because he mentioned that the presentation is crystal clear.
Oh my god.
So I think he got to answer this one question.
Yeah, Cairo got to prove to us.
Oh my
Yeah.
god.
Hello.
Yeah,
All right.
please.
Yep.
Is it the technique is non-wrap around facing?
No, we are building a 65-degree slope.
Or so the formwork is
Formwork.
one of the
So
technique for
yeah, okay. Maybe I explain a little bit on this part again. You see, if we are construct the slope for the slope angle up to 45-degree, so meaning that we are doing like 30-degree, 35-degree, 40, 45, then we can use a non-wrap around technique by installing the geogrid layer by layer at certain intervals. So that is up to 45 degrees. If we want to build something 45 degrees onward, like 45, like 50 degree, 60 degree, 65 degree, 70 degree, 80 degree, then we can use the wrap around technique by having a facing like formwork or the backworks, or we can even use a steel mesh as a facing to do the 65 slope as in this question. So I already answer question number 3, Cairo.
Sir, that means if the slope is 45 degree and above until 70 degree, so we just need to use the wrap around facing. Is there any techniques that we can use?
More than 45.
Yeah,
For example,
45. So,
more than 45, then wrap around. You can design it using this technique.
Chimbut, if you don't mind, can you please go back to the slide so that it's easier for the students to refer? I think they're trying to graph that particular slide that shows
slide 11.
a combi.
I think so.
Okay, so everyone can see, yeah?
Yep.
Yeah.
So we can see if for slope less 45 degree or less than 45 degree, so we can use a non-wrap around facing. So if it's for a slope more than 45 degree, for example, 50, 60, 65, or 70, and so on, then we can use the backwork, formwork, or the steel mesh. So
Right.
these are the answer for the question.
Okay, thank you, sir.
Yeah. Okay.
Next
Good.
question.
Yeah. Anyone else to try the remaining questions? 3 more to go.
Yeah. Next question, please.
So question number 4. Please list the possible failure mechanism in geogrid retaining wall.
Anyone would like to try?
Is it based on the
Wait, Cairo again? Is this Cairo?
failure?
Cairo, come. Let's give other people a chance, okay? You'll be answering all the questions otherwise. Okay. But thank you for the participation. All right, let's see. Is Wei Fen, Ling Wei Fen, are you here?
Yeah.
Hello, Ling Wei Fen. All these students all putting up, just turning it on without being there. Come on, Wei Fan, are you there? No.
Yeah, Wei Fan.
Oh, siapa satu kumpulan dengan Wei Fan? Boleh tolong jawabkan? Who is of the same group as Wei Fan? Tak mengaku pula. Tak dari kumpulan dah. No?
Yep.
Mohana, are you there, Mohana? Mohana? Wow, Cairo looks like you're the only one online.
Is it the overtuning or the base sliding?
Amar, Amar is
That
answering.
is the external stability that we concern about the geogrid reinforced soil structure. But over here, my question is, what is the possible failure mechanism in geogrid? The geogrid, what is the failure mechanism when it is in the reinforced retaining wall?
Is it rupture failure?
Yes, right. Number one. How about the other? We have three. We have three.
I'm not really
And
sure about
then-
the other technical terms, but rupture is related to the geogrid being not strong enough,
Yes.
correct?
Yes.
The other one is due to the geogrid not being the number of geogrids is not in.
Okay.
Hello?
Yeah. Yeah.
And the geogrid not being long enough, if I'm not mistaken.
Yeah. Not being not enough. That is a pull-out failure.
Right. The third one, if I'm not mistaken, based on what I jotted down, it's because the number of geogrids is not enough, but I'm not really sure about the technical term used for it.
Number of geogrid is not enough. Is probably consumed to the rupture failure also.
Oh, I see.
It's either we increase the strength of the geogrid or we make the geogrid spacing closer to each other.
Right. Thank you.
Yeah. So the third one is the connection failure at the facing. We're talking about if we are talking about the retaining wall, as we see in the slide. So okay, I think she has done a good work also, good job also. Thank you very much for answering. So number 5. Please
Yeah,
name
anyone,
two
number
partial
5?
factors in deciding the long-term design strength.
Come on, guys.
Yeah, come on, guys.
Come on, guys.
Or
I've
Dr.
done my
Jimmy,
part.
maybe you can just pick up one or two names. One name first. Maybe.
Yeah, I picked up a few names, but they are ignoring me. Okay, let's try again.
Yeah.
Fitri. Muhammad, no Fitri? Fitri ada? Fitri? Hello? No? Duan Kai. Go Duan Kai.
Yes, hello.
Yes, very good, Duan Kai.
Doctor.
Come on. Number 5. What are the two partial factors?
Find the answer, but I can't find it.
Huh?
I try to find the answer already, but I can't find it.
Is it not in the equation?
You can. There's only one equation in my slide. I don't
Yeah,
have any equation for you.
No, I find the
Doctor,
Who is this, please?
Sharon,
Okay, Sharon.
the answer for question number 5, is it the creep structure strength?
Okay. Then
The,
and what else?
then
What
the
else?
site damage, also the durability.
Yeah. Okay. So we can see here. This is the formula in deciding what is the long-term design strength that we use for the reinforced soil structure design. So PC is concerned is a creep rupture strength. The one we got it from the lab and the specification. So in design is concerned, we still need to add a different partial factor. For example, the manufacturer or the extrapolation factor, the site damage factor, which is the installation factor, and the other one is the durability partial factor. These are the answers actually. It's actually in this slide. So what you have answered also correct, but when you refer to creep rupture strength is concerned, it's actually the strength that we use to design, to calculate the design strength. Yeah.
Okay, thank you, Doctor.
Yeah. Okay, I think all the 5 questions has been answered. So yeah, Dr. Jimmy, so what is next?
So, Mr. Chan.
Yeah.
Dr. Chan,
Yeah.
So
we not hear you.
if we got any question later, we could ask in your email, right?
Yeah, can. You will have further question about the presentation today or about geogrid reinforced soil structures, then you can email me.
All right.
Okay.
Thank you, Mr. Chan, this session today.
You're welcome. You're welcome.
Mr. Chan.
Yeah.
I have a question for you, but I'm not sure whether it's applicable to what you explained just now about the geogrids. But in one of your slides, you mentioned there's a dongle or software known as Tensar, correct?
Okay. Yeah.
And Tensar Pave, right? Is it able for pavement innovation? Because based on what I've read a little bit, this Sunway Paving Solutions, they've come up with a permeable pavement, but I'm not really sure what they use to create the permeable pavement because I think due to confidentiality purposes. So, for Geogrids, right, is it applicable for these type of permeable pavements? Opinion?
Yeah, like we said, one of the application of Geogrid, which is not covered in today's topic, but one of the application that we can use it for the pavement optimization. So when you say that like Sunway system permeable pavement or like paver block pavement or the flexible pavement system and so on,
Yeah.
you can use the triaxial geogrid. Remember, I have types of geogrid
Yes.
for this application, which is the pavement optimization
Mm-hmm.
or maybe the ground stabilization. Okay, so that type of geogrid we can use this one.
The triaxial one.
Yeah, the triaxial. So this one usually we can install it above the subgrid, which is below the sub base and below the road base. Okay, to increase the stiffness of the pavement structures. Okay, I'm not sure that whether you all have gone through the pavement design, maybe using the Astro method, for example. Then you will come about something like equivalent standard axle. That is the unit to measure the numbers of the traffics. So, for example, we are designing a road for a 1 million equivalent standard axle. We will call it ESL. So to 1 million ESL. So in your design, there are few elements in the pavement structure. One is the formation, which you call it as a subgrid. Okay. Then we have the sub base maybe, and then we have the road base, and then we have the ACBC, the binding cost. Then we have the wearing cost for the asphalt concrete layers on top of it. Okay, so these few layers, when you put it together, you form a pavement structures. So the function of the triax geogrid is actually to provide the interlocking and confinement to the stone, to the stone that we install in the layer, like the sub base and the road base, kasharan or some granular material. Okay, so this interlocking and confinement is able to increase the stiffness of the road base and sub base layer. So after the stiffness is being increased, then the structure number of these two layers will be increased also. So when through some what do you call the improvement factor of, so we know all this, we learn all this improvement factor through all the trafficking tests we have carried out in our research. So that you have a higher structure number. So when you put into the calculation, if you maintain the thickness of the pavement, then you will have a higher equivalent standard axle, meaning that a longer life for your pavement.
Oh, I see.
In other way, if you want to save cost, for example, so you can reduce the thickness of your pavement. For example, you can reduce the thickness in your road base and sub base by putting in the triax geogrid. So this is the other way you can achieve as well. And we have another topic which can cover it, but I believe my colleague should have shared with you probably last 1 or 2 weeks, right, Dr. Chiming? Regarding this.
Tasha, you can refer to the slides and the lecture by Dr. Lok. That's just last week, actually, Chimbun.
Okay.
So we are, yeah. So because the focus of Dr. Lok's talk was actually on using the triax geogrid for road pavement improvement. Right? Remember that?
Yep.
And it's very much about interlocking and how this shape or this triangular shape kind of a structure will actually help to hold your granular materials in place, like what Mr. Chan has just said. To build a flexible pavement, the material used in there are all simply put stones. All right. If they're stones, that means they're granular, berbutir lah, sebiji-sebijinya tu, and they're angular. So they on its own, they are already interlocking themselves when you compress. But when you have this geogrid in there, it will give it extra stiffness and extra strength. Right? And hence, if the strength is improved, you could reduce the thickness of each layer, so that was in a way will save the cost. All right.
Okay, thank you.
Yeah. So the answer is yes, but you have to use the right.
Anyone else?
You have to use the right geogrid products.
All right, noted.
Yeah.
Right. Is there any more questions?
Yep. Actually, I was hoping that someone will ask me a question on the case history. Okay, for example, this one. Okay, no one asked me why in this case we are building the slope in the steeper angle rather than the like 45 degree. Why we have to use this one? Is there anyone can answer me that? Okay, the reason is if we go back to the slide here, we can see that this slope is actually very, very near to the railway line. So the answer, if we use this reinforced soil techniques to build a slope like 45 degrees and whatsoever and so on, it will have the slope will have very, very near to this railway line. So we are trying to keep the reinstated slope away from the railway line. So that is one of the factors when we consider the steep slope proposal and construction. So this is something that we can decide and choose what type of structures. When we talk about the types of structures, then this is something we can decide on site whether we want to build slope system, wall system, or the combination of both. Okay, of course, by putting wall also can be done to achieve the requirement, but in terms of the cost is concerned, might be higher than the steep slope.
All right.
Yeah.
Okay, the case, the point has been highlighted by Mr. Chan just a moment ago. It's actually a lot of it is about the site condition, right?
Yeah,
As you can
yeah.
see, yeah, ideally under normal circumstances, we would have chosen the normal stabilization method, just put in the geogrid. But in this case, because the railway embankment is already there, and we want to keep the rail track slightly away from the slope for safety purposes and all. Hence, we have to improvise the method, right? So this is where the site condition will determine whether what we plan on paper can be implemented on site. Alright. Ada lagi tak soalan?
Yep.
If not, I think we wouldn't want to keep Mr. Chan here for any longer. It's already he has been with us since 1:30 actually. So this is stretching on to 2 hours plus now. So if that's the case, thank you very much, Chin Boon, for spending the afternoon with us. In fact, Chin Boon has spent many hours to prepare these slides for you. So if we were there in presence, face to face with you, we have given you a round of applause. But now, just I think students, if you could. Turn on your mic and just show your face and say thank you, right? Let's just say thank you together, right?
Yeah, thank you very much.
Okay. So with that, I think we can let Chin Boon go. The students stay for a bit because we have a bit of discussion to follow up from this. Okay.
All right. Thank you.
Thank you, Chin Boon.
Thank you, Dr. Chan. Thank you, Dr.
Thank you so much.
All right. Okay. Stay safe, everyone. Have a good day. Okay. Bye bye.
Thank you.
Thank you.